Hi, in this video we consider a method that allows us to find the maximum or the minimum of a continuous function on a closed interval. There is a theorem in mathematics due to Weierstrass that says that a continuous function defined over a closed interval will always attain a minimum and a maximum within the interval. If you're wondering what a closed interval is, it is an interval that includes its endpoints. When we say that a minimum is attained, we mean by that there is a value of x in the interval for which f of x is the minimum, and the same would be true about the maximum. In the figure, we see the graph of a function. It has a relative maximum and a relative minimum within the interval where the tangent line is 0, but overall the global maximum on the interval is attained at the right endpoint b, and the global minimum is within the interval and coincides with the relative minimum. If we add the extra assumption that f is differentiable, then unless the maximum or the minimum occurs at the endpoints of the interval, the derivative at any optimum will be 0. This is the case in our previous figure. The function was differentiable everywhere since there were no corners on the graph. We can optimize by comparing the function values at any point where the derivative is 0 and where there's a corner, and also at the endpoints of the interval. So doing this, we're applying the so-called closed interval method. So recall that values of x, where the derivative is 0 or where there is a corner, are called critical numbers. So to optimize, we are going to evaluate the function at the critical numbers and at the endpoints and choose those x values with the smallest and the largest function values. You might now wonder why we need continuity in the assumption of the theorem and why we need a closed interval. Let's consider cases where the conclusion of the theorem would not hold if one of those assumptions is not met. In this first example, we are optimizing a function on the closed interval minus 4, 4. Clearly this function is not continuous. There is a jump discontinuity at x equals minus 1 and an infinite discontinuity, or if you prefer, a vertical asymptote at x equals 2. There's no minimum on the interval since the function near the asymptote goes to minus infinity. There's no value of x where we attain a maximum, that is no x for which f of x is the maximum, since at x equals minus 1, the curve has an empty dot where it is the highest, so no x for which the y-coordinate of that point is f of x. We say that the maximum is not attained here. This would not have been possible with a continuous function defined on that interval. So we need continuity if we want the maximum and the minimum to be attained. On this slide, the function is continuous, but we are optimizing over all real numbers and not on a closed interval. This function, which is e to the minus x, goes to infinity at minus infinity and has the x-axis as an horizontal asymptote. Therefore, the function gets as close as we want to 0 without ever reaching it. So in other words, 0 is never attained. So here our function does not have a maximum or a minimum, and this is due to not having a closed interval. This last example, we have defined e to the minus x on the open interval minus 1, 1. And as you can see, because the function is not defined at the endpoints, we have empty dots on the graph. Now once again, the function does not attain any maximum or minimum on this open interval. But if the endpoints would have been included, those maximums and minimums would have been attained in minus 1 and 1. So we see that we clearly need continuity and a closed interval for the conclusion of the theorem to hold, or for the closed interval method to be applicable. Now in the next two videos on global optimization, we look at examples where the closed interval method is used to obtain the maximum and the minimum. Thanks for watching.